Today we have two talks. So this is our last day for this virtual workshop. And the first speaker is Blaise Goutéraux. He will tell us about normal charge densities in quantum critical superfluids. Please, 45 minutes.
Thank you very much for the introduction, and thank you very much for organizing the conference and taking everything online. Okay, so today I want to talk about superfluids, and the specific aspect of superfluids that I want to focus on are normal charge densities. And I'll tell you a little bit why I think these are interesting to discuss. Okay, so some references and acknowledgments. So this is based on some recent work. This paper, sorry, there we go. This paper, together with Eric Mefford, who is a postdoctoral fellow at the École Polytechnique, and also some ongoing work that should be out soon. I also want to give special thanks to Thomas Andrade and Richard Davison, with whom I had started discussing these things a long time ago, maybe 3-4 years ago. Okay, here's the plan of the talk. I will start with a brief review of superfluids and superfluid effective theories, and in particular the hydrodynamic formulation. Then I'll give you a very brief, even briefer review of holographic superfluids. And then I'll turn to the main part of the talk, which is the holographic computation of the normal density. I will tell you a little bit about previous results and tell you about our main results. And then if time permits, but that's not entirely sure, I will link this to recent experiments on high TC superconductors, which were another inspiration for our work. So, as you probably very well know, superfluidity arises from the spontaneous breaking of a U1 symmetry. The condensate transports mass and charge without friction. And we can model this order parameter, usually with a complex scalar that has a Mexican hat potential that acquires a VEV. Of course, this is some kind of effective description that needs to emerge from the more macroscopic model that you want to study. Now, in this complex scalar, the VEV of the condensate is given by the modulus, and the phase is a gapless mode. What this means is that you can excite it without energy cost. It has a linear dispersion relation, and this is the Goldstone boson that arises due to the spontaneous breaking of a symmetry. Now, if we turn to the long wavelength low energy dynamics of superfluids, it's known since a very long time ago that they're very well described by the so-called Landau-Tisza hydrodynamic model. And this is the generalization of the usual fluid hydrodynamics to incorporate this new degree of freedom that I was mentioning, the gapless mode, the Goldstone mode. So all we need to do is consider the equations of fluid hydrodynamics, which are the conservation equation for the stress tensor, the conservation equation for the current. And then to this, we should add an equation that governs the dynamics of the Goldstone, which is this one, the so-called Josephson equation. And for relativistic superfluids, this is simply written as the contraction of u mu, the fluid velocity, with d nu phi, so the derivative of the Goldstone. And this is set equal to the chemical potential. Now, the Goldstone does not just add another equation to the system. It also enters in these equations because it will modify the constitutive relations and the thermodynamics compared to fluid hydrodynamics. So one disclaimer, throughout the talk, I will only discuss ideal order. Of course, the generalizations to dissipative order, to like first order and gradient, etc., are well known. But for the purposes of this talk, I only need to discuss the ideal constitutive relations. And so these are as follows. As you can see, for the stress tensor, we have the usual fluid part. This is exactly like in fluid hydro. And then there's an extra term due to the Goldstone. And the same for the current. Now, both of these terms are proportional to some coefficient that I've called rho s, which is the superfluid density. The superfluid density is the stiffness of the order parameter. It tells you how hard it is for this parameter to fluctuate. And it participates in the total charge density that I will call rho for this talk. So you see that rho is made up of two pieces. There's a rho normal and a rho superfluid. The rho normal, you can think of as the fraction of the total charge density that carries the normal flow, the normal fluid flow. And the superfluid density is the part that transports the Goldstone mode.
Blaise, can I ask a question?
Yes.
Why the coefficient of the extra term in T mu is the same as the coefficient of the extra term in J mu?
I think that, yeah, that's just for consistency. It couldn't be any other term.
What's wrong if I put these coefficients different?
Then you don't verify the first law. This guy.
Okay.
Yeah, so all of this is fixed. All of these equations are completely determined by thermodynamics. So there's no freedom here. Okay. So there we go. So the Goldstone appears in the constitutive relations and in the thermodynamics. And the important part is that you can think of this superfluid hydrodynamic description as the superposition of two types of flows. A normal flow, which is captured by this coefficient rho n, the normal charge density, and a superfluid flow, which is captured by the superfluid density. So of course, this also has important consequences on the spectrum of hydrodynamic modes. In particular, we see that there is now a superfluid sound mode that appears, which mixes the Goldstone and the usual charge diffusion mode. So by this, I mean that there's a new mode in the spectrum, which has this type of dispersion relation. So here, there shouldn't be a square, of course. So it's linearly dispersing in the wave vector, and the coefficient is called the speed of sound. Now, in fluid hydro, we would have ordinary sound, which would transport pressure waves, dP over dE. But here, because of the Goldstone, because the Goldstone couples to charge, it makes up a new sound mode. And this sound mode has a velocity, which is given by this type of expression. So you see that it's also completely controlled by thermodynamics. Here, S is the entropy density, rho the charge density, T the temperature, mu the chemical potential. There's another type of sound that people sometimes discuss, which is superfluid force sound. And it's the sound velocity that you would obtain if you held the normal component still. So you prevent the normal flow from flowing. And then you would get a slightly simpler expression. All right. So this is hydrodynamics. So in particular, it doesn't determine any of these coefficients that I've just discussed. It just tells you how they're organized in the equations that govern the system. So if you want to compute them, then you need to plug in some microscopic data. You need some model where you can compute these things. So in particular, since hydrodynamics is an IR description, it's a long wavelength, late time description, its parameters. So for instance, the normal and superfluid densities, which are IR parameters, they are not necessarily related in a simple way to UV parameters. For instance, a UV parameter would be, if you have a microscopic model, the number of atoms that are making up the superfluid, that are condensing. This is a UV parameter. And in general, there is no simple relation between these two types of parameters. And I will give you concrete examples of this. However, a very well-known example is that in helium-4, the condensate actually contains less than 10% of the total number of atoms. Yet, as I will now explain, the normal density vanishes. So the system is entirely superfluid at 0 temperature. There's no normal charge left, but only 10% of the atoms are in the condensate. So again, keep this in mind, IR quantities versus UV quantities. So in the case of helium-4, it's textbook material to compute the normal density. you can just do a weakly coupled calculation, assuming both statistics and Galilean or Lorentz boosts. And then the result that you would directly find is that the superfluid density at 0 temperature is equal to the total density of the system. And as I've already mentioned, that the normal density vanishes. Furthermore, so what this means is that at 0 temperature, the system is entirely superfluid, and you only need to take into account the Goldstone in order to write down the low energy dynamics. You can improve this calculation by going to small temperatures, and then you would find this result. So you would find that the normal density goes like T to the 4, then there's a factor of C to the 5th. C is the velocity of the Goldstone mode. The starting point of this whole calculation is that you assume that there's a mode that disperses linearly, and C is the velocity of this mode. And moreover, you can also compute the entropy density due to the Goldstone mode. And then this would allow you to find a very simple relation between the normal density, the entropy density, the temperature, and the velocity. So at the end of the day, you get this very simple relation that rho n is S times T over C squared. And this is, of course, up to corrections. And these corrections are corrections in temperature or in the value of C. Here, you're assuming that C is small, for instance, compared to the speed of light. Okay. So this is the standard result. Now, you can plug in these results in the expressions for the sound modes. And for the normal sound, so this guy, you would find that this is just C. So your linearly dispersing mode is actually governing the speed of normal sound. But for the superfluid sound mode, you would find a slightly different result. You would find C squared over 3, which actually happens to be C squared over D, where D is the number of spatial dimensions. And this is a famous prediction by Landau for the low temperature behavior of second sound in these spatial dimensions. But importantly, it relies on this guy going to 0 at 0 temperature in the way that I've shown on this slide. So now you can recover all of these results more rigorously, either in quantum field theory. You could write a quantum field theory of a complex scalar with a quartic potential, or also there's some very nice work from the early 2000s from Dan Son that wrote down a quantum effective action formalism for relativistic superfluids. The starting point is that you write a Lagrangian, which is a function of x. X is the square of the, x is d phi squared, and P turns out to be the thermodynamic pressure. And then from there, you can just calculate all of these quantities. This has been generalized to small non-zero temperatures by Nicolis. And more recently, it was checked that the normal density computed in this formalism gave you this kind of expression. So they don't really do the calculation in the paper that I refer, but I've talked to Luca de la Creta, and he checked that this expression was true. So in particular, you see that there's a small difference compared to the non-relativistic calculation. There's an extra term that you can neglect, of course, if C is very small, which is the limit in which this calculation here is usually done.
Blaise, one question.
Yes.
What do you mean by effective light velocity? Do you mean the velocity of the Goldstone mode?
Yeah. So they start by assuming that, so not here, of course, but in this calculation, yeah, let's see. Here, they start by assuming that there's a mode epsilon q, which goes like CQ plus high order contributions.
And this in general, sorry, yes.
And then you just compute, the pressure using both statistics, the entropy from the pressure, and then the normal density from computing from the superfluid hydrodynamics. So you just solve, integrals of log of 1 minus e to the minus e over kVt, etc. But you assume that there's this C here. So actually when you, and then, sorry, The way that this C is related to this CIR, here we see in the effective quantum, in the quantum effective action formalism, C really is the speed of light. But it's the speed of light of this particular effective theory, of this one, which may not be the UV speed of light.
Sorry, why do you call it speed of light? It's the speed of the Goldstone, the waves of the Goldstone mode.
So, well, you see that here, people were being a bit imprecise in the sense that they assumed that there's a linearly dispersing mode, but then when you actually go, then we know what the spectrum is. The spectrum is, there should be these particular sound modes. These are the sound modes that come out of superfluid hydrodynamics. And you see that this C is actually not really the second sound mode. It's related to it, but it's not exactly that. Let me put it this way. It's like you start from a quasi-particle description, and then somehow you're able to go to get the modes out of there, the collective modes. Let me say it even differently. I think it's clear. It's a bit clearer here. Here you would start from this effective action. Here you're assuming Lorentzian boosts. So there's a speed of light. The speed of light I'm calling CIR. The reason I'm calling it CIR is that this is an effective theory. So it's an IR theory.
Sorry, Blaise, but what you call the speed of light is the speed that enters when you define x d mu. It's the speed that enters there, but it's the speed of the waves of phi, not light. There's no light here.
Well, there is, because once to get to this result, then you assume, I mean, you turn on temperature, you assume Lorentzian boost. There's a boost symmetry.
Yes, but the boosts don't have to be with the speed of light. They have to be, they could be with the speed that appears here.
Let me say it in a different language. When I'm going to talk about holography, I'm going to consider flows that interpolate between a UV ADS4 and an IR ADS4.
But they don't have, but even
and
in
they don't have the same speed of light.
Right, precisely.
And so this CIR is going to be the effective speed of light of the IR ADS4. Does that make it clearer?
Sorry, Blaise. I think
Yes.
Elias' comment is just that basically that is an emergent IR speed, which can be whatever. For example, can be the Fermi velocity or can be in graphene speed of the light cone, but it's not related directly to the speed of light as a UV, let's say, relativistic speed, right?
Yeah, but I think that's also what I'm saying.
Oh, okay.
Yeah, I mean, I agree. This is what I'm trying to say, that when we write this effective theory, this is an IR theory. So it has an IR effective speed of light.
So it's just the speed of the light cone that emerges there in the IR theory.
That's correct.
Okay, I see. Thank you.
Okay, let me continue. So if we want to go beyond these EFT descriptions, then we need a more microscopic model. And for instance, people did this type of computation in BCS superconductors, and there you find that the normal density that you can compute, it's exponentially suppressed at low temperatures. And that's just a reflection of the BCS gap, the fact that there's a hard gap. But ideally we'd like other data points. And we'll get them by using holographic models of superfluids. So let me very briefly review holographic superfluids. It's known now since 2008 that we can realize a superfluid in the boundary by spontaneously breaking a U1 symmetry. And originally this was done by coupling a charge complex scalar to gravity. So this is the charge complex scalar eta. It has some potential V, and there's a Maxwell field in the bulk and the usual gravity term. And what was found is that at low temperatures, this complex scalar condenses here in a region which is close to the horizon. And this leads to a space-time that has this lump of charged scalar field that sits outside the horizon and sources some electric flux through the bulk and contributes to the total charge density. Now, the original solutions that were constructed by then were very soon after showed to obey this Landau-Tisa model of superfluid hydrodynamics. So, you know, we could be very happy because it's another, this is a good cross-check that the holographic models are doing what they're supposed to be doing. And the specific thing I want to do here is compute the normal and superfluid densities in these holographic superfluids. There was some previous work early on by Herzog and Yaram, and I will come back to it. So for this, what we need to do is we need to extract the one-point function, ttx and jx. These are the simplest roads to compute rho s and rho n. And from superfluid hydrodynamics, you can easily work out that they take these expressions. And then we need dx phi, but this will just get for free by a gauge transformation. So computing these one-point functions is easy using the usual holographic dictionary. We know that they're related to the perturbation of bulk fields delta Ex and delta GTX. And we can just set omega and q, so zero frequency, zero wave vector in the computation. Because this is, at the end of the day, this is really just thermodynamics. There's no dissipation here. I mean, there is dissipation, but I don't care about it. I don't need it in order to compute rho s and rho n. So this is essentially what we're going to do. We're going to solve the coupled perturbation equations for delta Ex and delta GTX. In d equals 3, this is what Herzog and Yaram did in 2009, and this is what they found. So here they were using, so Q is the charge of the complex scalar. So this is d mu phi minus iq a mu, the covariant derivative. And u is some parameter. They were using a quartic potential. So u is one of the parameters in the quartic potential. And so they scanned the parameter space varying q and u. And what they're plotting this is maybe if I blow it up, this is rho s over rho versus t over tc in both cases. And you can see that as they vary the parameters, well, there are a whole bunch of them where you see that at low temperatures, rho s goes to rho. So for all of these values, and here the same for these red curves. So which are
Blaise, can you say what happens if you increase u? What happens to the potential qualitatively?
I think u is the coefficient, is the quartic coefficient. So it becomes steeper, I guess. But I will come back to it. I will come back to, if you give me a few slides, I will come back to what happens when you increase u. So the only thing I want you to notice at this stage with these two plots is that, as you can see, that there are data points where it doesn't look like at zero temperature, the superfluid density equals the total charge density. And this is not a numerical glitch. So the question we'd like to ask is why? Because we've spent 13 slides discussing cases where the normal density vanishes at zero temperature. So this seems a bit surprising. And in the paper, they observed this, but they didn't really comment further on it. So we're going to redo their calculation and try to understand a little bit better what's going on. The strategy we'll follow is that at low frequencies is the following. At low frequencies, we have the hydro prediction for the current retarded Green's function, so GRJJ, this guy, at ideal order. And this is simply rho n squared over st plus mu rho n plus rho s over mu. So there are two pieces, one from the normal fluid and one from the superfluid. This is from hydro in the low frequency limit. Holographically, we know how to compute this object. this is just this ratio of terms in the UV expansion for the perturbation delta AX. Now, it's also well known that this omega equals 0 term in the retarded Green's function is given by the solution to the omega equals 0 limit of the delta AX equation of motion, which is the regular one at the horizon. So remember, every time we're solving second order differential equations in the presence of a black hole horizon. So there are always two kinds of solutions, one of them which blows up at the horizon, that's the singular solution, and another one which is regular at the horizon. The one which is singular is typically related to dissipative coefficients, and so that's not the one I want. I want the one which is regular. So we'll solve the delta AX equation of motion at 0 frequency, and we'll look for the regular solution. And since we want to focus on the low temperature behavior, we'll compute this regular solution in a small temperature expansion. And this will give us access to the normal density. So that's the strategy. Let's do a warm-up without a condensate first. So this is the delta AX equation. It looks slightly complicated. You don't need to worry too much about all the terms. This is my convention for the metric. This capital R is simply the electric flux at some radial hypersurface in the bulk. And because I have no condensate right now, I've turned it off for the time being. So eta equals 0 for now. Then this electric flux is simply just the charge density in at the boundary, but it's also the charge carried by the horizon. These quantities are equal. So the way I've written this equation, this is maybe a slightly unusual form for people that are familiar with this type of computations, suggests that I can expand it at low t in powers of st. So let's do that. I'm defining this calligraphic A as follows. This is the chemical potential times AX, that's the regular solution, so that probably should have a delta. There we go. Delta AX over delta AX naught. Delta AX naught is the boundary value of delta AX, divided by AT, which is the background value for the gauge field. So then I will expand this in powers of st. And I wish to solve this order by order, imposing regularity at the horizon. So let's see what this gives. If you solve it order by order, you can find the solutions order by order. The first one is very simple. It's A0 equal 1. Then I have an integral solution for A1. Then I start having nested integrals for A2, etc., etc. Importantly here, we have constants of integrations that are allowed. And we should fix them such that delta AX is regular at the horizon. Now, since delta AX is roughly AT times A, and AT vanishes at the horizon, like R minus RH, this means that I'm allowed to have some mild singular behavior for this calligraphic A. However, what's not guaranteed is that I can do this, that order by order in ST, rather than on the full resummed A. It's not clear that you're allowed to do this. But in this case that we're discussing, it turns out to be consistent. And here's the reason why. The reason why, maybe let me discuss it here already. So for the case without a condensate, you can actually find a closed form expression for delta AX, for the regular solution. It's just this. So you can plug this expression in that equation, and you would find that it is a solution. And moreover, this is manifestly regular at the horizon. So from this, we would directly be able to extract this expression. Then you can expand this order by order in ST, and you would find this type of expansion. Now, it turns out that from our expansion in ST, so solving for these calligraphic A's, we get precisely this. I've not written the order ST squared term, but the agreement persists at higher orders. So all this to say that for this case, without a condensate, we could, our task is actually simpler than it looked like because we could find an exact expression. But for the case without a condensate, we won't be able to. There won't be any closed form expression. And so the only thing we'll have that we're able to do is either numerics or this expansion in calligraphic A in powers of ST. So this is a cross-check that our expansion is well defined, that it works. And this is a cross-check in the case without a condensate before we move on to the case with a condensate. So let's do that. Now, once we have the condensate, we have a new term, which is this guy on the right-hand side of the equation. And with a condensate, now this R, so this is still the electric flux, but which at the UV gives me the total charge density, but at the horizon, it gives me only the charge behind the horizon. It doesn't measure the charge that's carried by the condensate that's sitting outside the horizon. And like I said, in this case, there's no closed form expression, mainly because this term on the right-hand side spoils the integration of the left-hand side. It used to be 0, so you got an integration for free. And so what we need to do is use this expansion in ST or to use numerics. So we'll do both.
Blaise, what is eta?
Yeah. Eta is the condensate. It's the complex scalar, the modulus of the complex scalar. So there we find very similar expressions to before. So this is the same as without a condensate. This is the same as without a condensate. But now there's an extra term at order ST squared. Yeah, just to be clear, this is order ST to the 0. This is order ST, and this is order ST squared. So we can expect that some things might be happening at order ST squared because of this extra contribution. So at second order, remember we have these C's here, C1, C1, C2, C2. These are all free integration constants that I need to fix in order to get a solution which is regular at the horizon. So at second order, whether I can consistently set them to 0, as I was doing for the normal fluid, depends on this last integral in A2. So this guy, which is boxed, and that depends manifestly on the condensate. If the integral converges in the IR, as you take the 0 temperature limit, then you can consistently set all the C's to 0, in particular C2 and C1 to 0. This you can just, if it converges, then once you evaluate it in the UV, then this will just contribute some constant times ST squared. So it doesn't spoil the ST expansion, if you like. On the other hand, if the integral diverges in the IR, then you need to keep both C1 and C2 in order to find a regular limit, and you need to fix them in a very precise way. So what this reveals is that the limit, the 0 temperature limit of rho n, of the normal density, it's controlled by the competition between two deformations of the ground state, the deformation that breaks particle hole symmetry and the deformation that breaks the U1 symmetry. Roughly speaking, it's controlled by the fact that I have a term that has this ratio, eta squared over r squared, where eta is the condensate, the modulus of the charge scalar, and r is the electric flux in the bulk. So to understand what happens to rho n into the normal density, the 0 temperature limit, we need to say something about the 0 temperature ground states of the model. We need to understand these deformations. So this is also something that's very well known. It was worked out in 2009, and Gupser and Nellor, and also Horowitz and Roberts, they showed that for the quartic potential, you could have two types of infrared geometries. Either an ADS geometry that has z equal 1, or a Lifshitz geometry that has z different from 1, where z appears here. Z tells you that time and space don't scale the same way. So this metric is invariant, and that t goes to, sorry, I'll try to write a little bit better. T goes like lambda z to the t, and x I goes like lambda x to the I. So for a Lifshitz space, there's an anisotropy between time and space. Now, whether you get one or the other in the IR, whether you get the ADS D+2 or the Lifshitz ground state, depends on whether the gauge field is irrelevant at zero temperature, close to the horizon, or not. So it depends on what the gauge field is doing in this region. So what does this mean? It means that let's imagine that you started from the IR ADS 4. So this is the ADS metric. Then what you do is you want to work out the behavior of the gauge field. So you plug this into the time component of Maxwell equations, and you solve for the time component of the background gauge field, AT. You'll get some power law, and then you backtrack this on the metric. And when you backtrack this on the metric, you get this type of expression where the ADS metric at zeroth order is corrected by terms that are sourced by the gauge field. And in order for your ADS4 solution to be stable, to be RG stable, then these terms, they have to decay as you go towards the infrared. They should vanish as you move towards this region, towards the horizon.
Oh, excuse me. What is the meaning of beta?
Beta is just some exponent. It depends on your theory. It's a combination of parameters. It's related to how the gauge field scales in the infrared.
It is positive or not necessary?
Exactly. So this is where you need to work out. So in the quartic potential model, this will depend on the coefficient of the terms. You know, the m squared term, the u term. It will be fixed by these terms. But then you need to compute it, and then you need to check whether it's positive or negative.
Mm-hmm.
So if it's negative, since my IR is R to infinity, if it's negative, then it's an irrelevant mode. And this means that this IR ADS domain rule is stable. On the other hand, if you're sitting in some part of the parameter space where it is positive, then this is a relevant deformation. It means that this IR ADS2 is RG unstable, and this is not the true ground state of your model. And instead, what you'll find is that the flow is driven to the Lifshitz geometry with Z different from 1. Intuitively, you can see it in this way. You're turning on a time component for a field, some AT. This wants to break the isotropy between time and space. You have a time component, so it doesn't want to stay isotropic between time and space. But whether it actually manages to do so or not depends on the sign of this beta. And there are circumstances where it becomes strongly relevant. And so the geometry just doesn't want to stay ADS, which is isotropic. How am I doing with time? I'm sorry, I can't see time on the full screen mode.
There are still 6 minutes or so.
6 minutes or so. All right. I'll try to speed up. Okay, so now we return to this integral in A2. So this guy. Yeah, this integral. And now we want to evaluate it on the IR zero temperature geometries and see what it does. And what you find is that for low values of Z, including Z equal 1 up to Z less than D plus 2, where D is the number of spatial dimensions, then the condensate dominates and this integral blows up, and so modifies you need to modify the regularity condition, and it directly leads to this expression for the normal density. And that is exactly the EFT result that holds at Z equal 1, except that here we see that we've generalized it also for values of Z that are greater than 1. And CIR is the IR speed of light, like I was saying. And we find that what dominates is the particle hole breaking term. And then the behavior of rho n completely changes. Rho n goes to a constant at zero temperature plus some subleading corrections that you can compute. So what this means that for sufficiently large Lifshitz exponents, the normal density no longer vanishes at zero temperature. And here, to return to the comment I was making at the beginning on UV versus IR parameters, here, for all cases, all of these cases, whether rho n goes to 0 or not, at 0 temperature, there is still no charge behind the horizon at 0 temperature. So in these space-times, as you take the 0 temperature limit, all of the charge sits in the condensate. And this is the UV parameter. And it has no direct relation to what ρn, which is an IR parameter, a parameter of the long. This is in 4 space-time dimensions, 4-dimensional bulks. So both of these cases have a ρn that goes like st over c squared, CIR squared, as I was mentioning on the previous slide. These are these solid lines, and the dots are the numerical lines, the numerical results. And z equal 12, so this is greater than d plus 2. ρn goes to some constants. And then we can also compute the subleading temperature dependence. And this is what we display here. We subtract the 0 temperature value and look for the leading scaling behavior, and we match this coefficient that we could compute. So this is just to convince you that everything is consistent, that this analytical approximation scheme that we have is working well. So the summary so far, and I think actually I will stop there, is that we've seen that ρn, the normal density, vanishes in holographic phases, where it's the condensate that dominates over particle hole breaking at low temperatures. And in this case, the calculation that we've done, it reproduces the expected result from the effective field theory framework for phases that have emergent Lorentz symmetry. But what we've done is we've shown that it can also be extended to phases that are Lifshitz invariant, provided that z is less than d plus 2. However, for phases that have a large Lifshitz exponent, then the normal density is non-vanishing. And as I've commented, this is unrelated to the presence of a charged extremal horizon or not. And these results explain everything that I was telling you about these previous results by Herzog and Yarrow, in the sense that now if you look at these choices, the choices of parameters that lead to these curves, then you see that all of these they correspond to Lifshitz ground states that have z greater than d plus 2. So that's why the normal, the superfluid density does not asymptote to the total charge density at 0 temperature. I'll leave you with some open questions. So we've shown this expression still holds for Lifshitz invariant phases with z less than d plus 2. And that there's some IR speed of light. And this depends on temperature in this way. So this is now a temperature dependent light cone velocity. This directly implies that the superfluid second sound mode vanishes at 0 temperature in this way. But at least this was for z equal 1. For relativistic superfluid, the starting point of the quantum effective action is that you have a Golson mode that governs the dynamics at 0 temperature. And now we see that its speed for Lifshitz phases vanishes. So I think it suggests that there's an interesting future direction to try to work out what is the equivalent to this quantum effective action, but not for relativistic superfluids, but for Lifshitz superfluids. Let me leave you with a teaser. I didn't say anything about high TC superconductors, so this is my teaser. Are there other systems that feature a non-vanishing normal density? Well, maybe, but you can either ask me or look it up in the paper where we discuss it more. Thank you very much for your attention.
Thank you very much for your very instructive talk. I guess not so many people from our community are working in these directions. It's make your presentation more interesting and more instructive. For me, it was very nice to listen to your lecture. Please, any questions?
I have a question.
Mm-hmm.
It is, you mentioned at some point that you have a perturbation expansion in ST, and then the two first terms, usually you have some integration constants which you set to 0 because they're regular. The rest of the solution is regular. But when the third term comes in, it may contain a divergence, and then you have to cancel it by turning on C1 and C2. Now, this seems a little bit strange because you will need to do that, I presume, with subsequent terms. Is that the case?
We didn't push it to higher order because the expressions become extremely messy. But yes, I would expect that all subsequent terms need to be fixed in terms of this C1. But at the end of the day, it's this C1 that matters, the one that appears at first order in ST.
But
and you fix
C1
C2.
is fixed in the end or not?
Yes. Yes, what you find is that you need to fix C2 in terms of C1, and then C1 to be actually, I didn't write this, but C1 is fixed to be the CIR.
I see. Okay.
And that is enough to get a regular solution.
Okay, thanks.
More questions, please?
Since there are no other questions, maybe I can ask another one. So can you tell us a couple of words about the possible applications of this that you mentioned?
So you mean to high TC superconductors or in general?
Yes.
I would say, so in general, if we could find superfluids that are Lifshitz invariant, then that would be an application. But okay, I'm not exactly aware of such superfluids. However, one of the motivations were these, like I mentioned, it came from measurements in high TC superconductors. So I'll tell you very briefly. So these are superconductors that are extremely interesting because they become superconducting at a much higher temperature than temperatures of conventional superconductors. So for now, the boundary, I think the frontier is maybe 160, 180 kelvins. But they're also very mysterious because they fall outside the BCS paradigm. You cannot describe them with BCS theory. So people have no control over what sets the value of the critical temperature, etc. And they've resisted theoretical description since they were discovered in the mid-80s. And they have a phase diagram, temperature versus doping. So doping has to do with their chemical composition, which looks like this. There's this superconducting phase, which is here, this dome. And this part, which is called strange, people don't really know how to describe. However, there's a part here which is believed to be more conventional, believed to be describable by a Fermi liquid. And in particular, the superfluid in this region was thought to be of a rather conventional nature, that you could do BCS here in this region and get away with it. But in 2016, Bozovic and his group, they published a study of the superfluid density in this region of high TC superconductors. And they reported two surprising features. One was that the magnitude of the superfluid density itself was extremely low compared to expectations, compared to the value of the normal, of the density in the normal phase. And I also found this linear behavior, whilst BCS theory would predict something like t².
Oh, excuse me, but I
Yes.
you. Is this experimental result?
Yes.
You experiment. Okay, thank you.
Yes. This is a set of experiments, and these experiments were confirmed by another set of experiments by these people. What they measured is they measured the frequency-dependent conductivity. So basically, the retarded Green's function of the current. And what I want you to see is this. Here what they show is that as you go from the normal phase to the superfluid phase, there's this drop is very modest. In a BCS superconductor, you would expect a big gap, this big exponential gap to open. And here you see that it changes a little bit, but not that much. And you can also see it more clearly here. This is plotting the ratios of, so this is the normal density. Sorry, this line here is the normal density. This is the, let me get it right. Sorry, it's the other way around. This is the, so this one is the density in the normal state. This is the normal density, so the object that I've been computing in this talk. And this is the superfluid density. And as you can see, the superfluid density, so the green curve, is not lying on top of the yellow curve, of the yellow dots. And this, the authors interpret as the signal that there are some normal electrons that remain in the condensed phase, that that the whole system does not become superfluid as you decrease temperature. So this was also our motivation to try to investigate whether we can understand a little bit better normal densities using holography.
So can we say that your result is kind of universal? That is, whenever you see this, automatically it means the existence of some appropriate Lifshitz fixed point?
So it doesn't necessarily have to be Lifshitz. I think it's, the statement is crisper when you have some scaling behavior in the IR, such as Lifshitz or hyperscaling violating Lifshitz, because then you can just look at the spectrum of deformations around this critical geometry, and then you can characterize whether the normal density should vanish or not, depending on which of the two deformations that I was mentioning, the particle hole breaking and the U1 symmetry breaking deformations is dominant. This is a very crisp statement.
But this is an RG analysis. But what I would like to understand, if you know it or if one can get it, is that this ratio is a property of the infrared fixed point, right?
That's right. Yes, this is the claim.
So what property of the infrared fixed point determines this?
I would say it's going to be the interactions away from the infrared fixed points. What type of interactions you have.
So it is not the property of the infrared fixed point alone?
No, not alone.
Okay, thank you.
Though, of course, the infrared fixed point itself influences the various scalings, right? But it's not the infrared fixed point alone. You also need to know something about how you flow away from it.
Okay, more questions? Okay, maybe I will ask just very simple questions. You start from some special metric, and there are some functions there, A, B, D, yes. I guess. How do you suppose to solve some equation for some Lagrangian, or you just take them to explain something? This is some general question.
So numerically, we solve Einstein's equations.
You start
coupled to the complex scalar.
Mm-hmm,
yes, we start. Sorry, so maybe this wasn't clear enough. Throughout the talk, the theory I'm solving is the theory for the original holographic superconductor. This one.
This one.
With a quartic potential.
I see. So you fix the potential.
Yeah. But you see that for the analytical calculation, we don't really need to fix anything until until we get to
the very end. Okay.
Until we get to this part, because then we need to know what this integral is doing. So then we need to know what these background functions are.
I see.
But even so, we don't need to know what they are everywhere in the bulk. We only need to know what they are in the near horizon, near extremal region.
I see. Okay. More questions, please? If not, let's thank the speaker again. Thank you very much.
Thank you very much.